You know, the notion that we're going to transition these exascale, these codes, these large-scale codes to exascale, just by porting them over and hitting a compile button isn't going to work. They have to be re-architected.
One of the biggest problems that we have right now is that the architectures that we will get for exascale are unknown. We really do not know what the chips are going to look like.
Are we going to be in a situation where we can simply take our codes or our algorithms of today and port them onto those architectures? Will they even run in the complexity of those architectures?
The biggest challenge as an application developer is going to be finding a way to write a code that performs well on exascale machines, but doesn't increase the complexity of writing the code so much that we can't produce them.
We think that other technologies like transactional memory and speculative execution are also going to be necessary for us to get good performance on these very more exotic kinds of architectures that are necessary for us to meet the computing challenges that we face in the years to come.
One of my beliefs is that GPUs are going to be one of the path forwards for exascale.
So this is really something we started talking about several years ago, as far as that we really need to co-design future architectures and applications together.
You really have to have this, at least this triad interaction of people who really understand the architecture, people who really understand the physics, and people who really understand the algorithms.
It's a multi-year effort by a wide variety of scientists around the country, many of whom are at the national laboratories, working with the computer vendors, trying to make exascale a reality.
Computational physicists are very, very patient scientists. We can wait months and months and months and months for answers. But imagine what we can do if we could cut that going from petascale to exascale by the factor of 1,000. We could get answers in hours instead of months. And that would transform the entire science from something that takes months to something that takes hours.
The calculations I'm running now on Cielo in 3D are state-of-the-art calculations on 32,000 processors. This is mind-boggling to me. We've never run on this many processors. The code is acting normally, running very well, and in fact we're able to run these calculations on this machine that we were not able to run on any other previous machine.
One of the complex world problems that we're really taking on here with the computer simulations that we're doing is looking at impact hazard mitigation. Very occasionally there's a threat from an asteroid or a comet that's orbiting through the solar system that threatens an impact onto the Earth. These are big objects, some of them. And so if they hit, they can really ruin your day.
Many countries are investing in exascale computing technologies because they believe that that is something that's critical to all segments of their society in terms of economic competitiveness and national security.
Now, so climate models, because of this great computational complexity, always have a way of consuming all the computational resources that one can use. Improving climate models will have real economic benefits to the United States.
It's a little bit funny that our largest supercomputers here, like Roadrunner, are based upon video game chips and architectures. But that's really what's driving the market. The market is being driven by commercial applications, and the biggest commercial applications of large-scale computing is the fancy graphics that goes on in video games. But we're using it in a way that best suits our national security needs.
Our applications have a lot in common with game physics. And so, you know, for example, if you're doing realistic ray tracing in a game, that is similar to running a Monte Carlo simulation where you may have a source that is radiating out heat.
The exascale machines that are being envisioned for tomorrow are going to require us to go to billion-way parallel. That's something bigger than we've ever done before, but it's not necessarily a bigger challenge than we've already achieved.
Exascale requires us to work on several daunting challenges simultaneously, such as electrical power consumption, the amount of memory we have to put in the machine, just the sheer number of components, perhaps billions of components, and programming for the machine.
Programming models may be the largest challenge that we face in moving to exascale systems.
It may require as much as, let's say, 100 megawatts of power to support an exascale system.
Because power is such a problem, it brings with it a number of other challenges that come with trying to do 1,000 times more work in the same power envelope.
There is a ton that excites me about exascale.
So by having an exascale machine, you could potentially do much larger calculations at that scale to reduce the uncertainty that is associated with the results of that simulation then that feed into a subsequent continuum or system level calculation. But since I'm an applied mathematician, what really excites me the most is the new kinds of algorithms that we can develop that specifically are targeted towards exascale architectures, which are likely going to be very different from existing petascale architectures.
It's really amazing getting to run on the latest advanced architectures here at Los Alamos. It's like getting the keys to the space shuttle, really. It's amazing what we're able to learn from that, from not having to make very cautious approximations, from being able to zoom in and really see how the small scale physics matters to a macro scale process is very exciting.
What excites me most about exascale is that for the first time in 20 years, I think the power problem is difficult enough that we could move supercomputing into a field that's actually leading computing again, rather than one that's sort of following a Moore's law vendor trend. That as you enter this phase where you're power limited and power dominated, the opportunities to re-architect the machine are tremendous.
My expectation is that we're going to open up a whole new world of discovery yet again, in increased predictive capability.
Oh, what am I going to be able to do in the future? Well, shoot, can I have a holodeck? Oh, it's so hard to predict, but it's so exciting.
Ready or not, exascale's coming. It's going to be really hard, but we have the people, we have the partnerships, we'll succeed.